muted. We are recording the webinar so I can share it with you later, and by keeping everyone on mute, we will ensure a high-quality recording. After the webinar is over, you'll receive an email with a link to this recording as well. If you have any questions, feel free to submit them using the questions field in the toolbar on your GoToWebinar application. If we have time at the end, we can address those questions, and if we run out of time, we can answer those through email. All right, so today's presenter is Terry Harris. Terry is the president of Reliable Process Solutions. He is a certified maintenance and reliability professional and a certified maintenance and reliability technician. Terry has worked in the manufacturing process industry for 26 years for a Fortune 100 company. Most of his time was devoted to maintenance area efforts, with most of his career being devoted to improving the reliability of his plant and other U.S. and European locations. Along with working as a facility maintenance and reliability leader, Terry was involved with many corporate-wide projects to cut costs and improve equipment reliability. For many years, Terry has devoted his efforts in applying his knowledge to critical pieces of equipment and processes within many industries with excellent results. Terry has performed training in the U.S., Europe, China, Singapore, Thailand, Canada, and Korea. Thank you for joining us today, and I'm going to pass the controls over to you now.
All right, thank you, and welcome everybody. Thanks for taking time out of your afternoon to join the webinar. It's an important topic to discuss some of the things we want to think we're doing as reliable efforts, that sometimes we don't follow all the processes that lead to some unreliability or some maybe not some of the results that we expected to get out of our efforts. So I'll cover a few of these. There's a lot more. We've only got a short time to do this, but if you got questions or after the webinar, like I actually said, go ahead and send an email. And have time at the end of the webinar for some questions. So a little bit about me. I'm a certified RCM facilitator. I have my own RCM process now that saves companies a little bit of money, a lot of time in doing the RCM effort. We do a lot of predictive and proactive training, a lot of lubrication and lubrication excellence training. And you can see the list. We try to cover a broad spectrum of processes such as maintenance audits to get you on the right track to build your reliability process. And then we also build some plug-and-play loop storage rooms, which you can see on the website if you're interested in those. So let's get started with the webinar. And I put on here, there's been a mad rush in the U.S. for the last 4 to 7 years, for plants to improve equipment reliability. In the last 2 years especially, it's been very, very busy for our company in performing a lot of the training and some of the specific reliability techniques that are needed to get you started. One of those being we do a lot of training. We sell some software in that area to make sure people are doing PMs and doing PDMs on their most critical equipment. So we kind of help you define what those critical processes and equipment are. And the reason we're trying to do this, where we have this urgency for reliability, is to be able to compete in the marketplace. We have companies all over the world now that are making the same products we try to make here in the United States. A lot of the businesses that I go into have lost a lot of their market share and lost a lot of their businesses to companies in China and other countries. Not just specifically for the reasons of lower labor costs, it's more for the reasons that they were kind of unreliable and they weren't doing the right processes to make themselves competitive. If you look at this picture, and I ask everybody when I show this picture, I train, who's going to win this race? And I ask the question, who's going to win the race to the top of the hill? And a lot of times we're going to look at the Lamborghini on the right-hand side and say, well, the Lamborghini, if we're racing to the top of the hill, I'm probably going to put my money on the car on the right. Now, if we're racing these all the way across the U.S. or all the way across Australia or Europe, there is a probability that the car on the left could win the race. It depends on a lot of factors, the same way it does in our operations. And I tell people this all the time, the first thing it depends on is the operator. If you put the wrong operator in the vehicle on the right-hand side, maybe they don't even make it to the top of the hill. I ask about maintenance that's performed on these two. If we do the wrong maintenance on the one on the right, they may not last very long. If we do proper maintenance on the one on the left, that in theory that vehicle could last forever. Then I ask about the cost of maintenance. The cost of maintenance of these two, the cost of maintenance on the one on the left is probably more than it costs to change, or you could probably change the oil on the one on the right for about the same cost you could change the engine in the one on the left. Then the last question I always refer to with this, looking at this picture, is which one of these is your plant? You know, is your plant a brand new 1-year-old Lamborghini plant, or is your plant or facility 20, 30, 40, and 50 years old? And those are usually the plants that I go into and try to help them out, trying to make them competitive. And we do that by maintaining them correctly, by operating them correctly, and doing all the right things right. And we try to make them competitive in the U.S. or world marketplace. So that's what all of that slide's about. It's just about competition and what we have to face in the industry today. Now, if we talk about processes, there's many processes and programs that we can attempt to use in our plants. You know, I go into facilities all the time, and they've tried to do lean maintenance or lean manufacturing as their first process in reliability. Well, the truth is you have to be reliable before you can be lean. We try to do other processes like precision alignment. We try to do precision balance. We try to do precision lubrication with lubrication excellence programs. But to do those, we have to have some fundamental things we do correctly, or those processes don't really work very well in the end, and we don't really see results. And what we're really looking for is processes that we can do in our facilities that actually show results in the end, either in more rate or in more lower cost. This is a question I'm asked by corporate people all the time. You know, is there one process that can take us to these higher levels of equipment life and equipment reliability? You know, is there a silver bullet out there? Well, there's really not, because every industry is different. Every one of these processes take you to different levels and do different things for you. So there's not a silver bullet thing we can do to take us to the end. I use this chart, and some of you have been on my webinar before have seen this. This is the performance failure curve. There's a lot of different models of this out in the industry. The one I use in my training is the one you're seeing on the screen right now, where the equipment performance for any piece of equipment is on the right-hand bar, which up at its peak performance or in the piece of equipment's new, we're getting everything out of it we can get out of it, and we're doing what it was designed to do. Across the bottom of this curve is time. And what this curve is showing, that as equipment wears and as equipment gets older, it reaches a point here where it starts failing. And if we're finding all of our failures by using these touching, noise, smell, and we're reacting to that data, you're going to be in the reactive mode, and you're only going to be 10 or 15% efficient or effective in maintenance. If we start using predictive technology where we can predict failures up here when they first occur in the equipment before human senses can tell, and examples of those are mechanical ultrasound, vibration analysis, oil analysis, wear particle testing, thermography, motor circuit evaluation, and non-destructive testing. If we use these technologies effectively and we actually react to the data, we can make our equipment last a lot longer and have less failures. Now, I've got these listed on there in order, but they're not in any order of importance. And the example that would be is if I'm looking for particles in my oil, mechanical ultrasound's not going to help me there, but oil analysis will. You know, if I want to know if my coupling's out of alignment, I might use vibration analysis, and later down the line when components start wearing, maybe oil analysis kicks in. But we have to use the right technology for the failure mode you're looking for. But what it's saying here, if we use predictive technologies effectively and we react to the data and plan the work and make corrections up here in this part of the curve, it keeps the component from getting to this wear mode in the lower part of the curve. Collateral damage, here's an example. You know, one of my customers where vibration told them that this gear in this gearbox had some wear. They didn't react to it. The teeth finally fell off and destroyed the bottom bearing in the gearbox. So we have to react to the data. On the far left-hand side of the curve, we have our proactive area, things you can do when your equipment's brand new or in its peak condition that keep it in that condition. Lubrication excellence, precision alignment and balance, buying the correct components for our critical equipment, the better stuff. You know, an example of that is in a study we did on electric motors. Toshiba makes a better motor because they have higher balance standards. They mill the feed off to within 1,000, so they use better insulation. More expensive motor for sure, but these are motors that, you know, the company I came from, we use these on our top 20% of our critical equipment to eliminate failures on those high dollar cost items. But you can see as you go down the line here, there's a lot of processes, and if we do these processes correctly, we become more proactive in our approach to maintenance and reliability, and our cost will eventually go down, and you'll have less reactive maintenance. And I always tell everybody, you don't have to be 100% effective or proficient in these tasks, but you have to understand them and use parts and pieces of every one of them. I've got PM task across here. You know, we're performing PM tasks no matter what area of the curve we're in, but you know, these PM tasks are going to get better, and they're going to change as we get better in our proactive maintenance area or better in our reliability process. And again, moving resources where we do more vibration analysis, more predictive and more proactive, moves us from that reactive area. As I travel from plant to plant doing training courses around the country, around the world, you know, more and more companies are adopting these predictive and proactive practices and techniques. You know, why are they adopting these? Well, and again, we talked about this earlier, to be more competitive in their respective businesses. If we do these things correctly, our costs go down, our production many times goes up, and we're more competitive. Well, let's talk about some efforts people make in a couple of these areas here. And like I say, we'll cover a few of them today, but you know, foundation and grouting practices. You know, very common construction practice during installation. If done correctly, it adds some reliability to our processes and our equipment. You know, here's a structure that a company's putting in to mount some equipment on. We're doing the grouting process ahead of time, making sure the frame's level, supporting the frame 100% to the floor. And when we put our equipment on here, you know, it should have less vibration, should have a lot more level surface to mount the equipment to, and it should gain us some reliability benefits. Here's a nice application of a plant where the pump foundations are poured on a concrete base. Everything's grouted in place, and these pumps are a lot more efficient, will last a lot longer due to this reliability technique. But there's some we need to look at in doing this is, one, after you pour the foundation, have to use these grouting techniques, making sure we use a good base to mount the pump on. So if you look at the base in the upper left-hand corner, the standard base you see in many industries, it's a rounded piece of channel. The surfaces aren't completely flat, so we have to do a lot more trimming, a lot more chance to be out of alignment in the alignment process. The other two bases show some bases that have machine surfaces to mount the motor on, machine surfaces for the component, whatever it might be, and we can do a lot better job of alignment, and the component is supported much, much better. And here shows the base with the machine surfaces, but it's also got alignment bolts on it, so we can move the motor around, you know, within a thousandth or two very easily without beating it with a hammer, prying it with a crowbar, and this gives us a lot more accurate alignment process. And again, you know, one of the things in mounting equipment, it says here the foundation mass should be approximately 5 times the mass of the supported equipment, supported machinery. So if you can imagine these 30-degree lines from the center of rotation, this is just one of those engineering practices we have to look at, making sure we get the component on a base that's actually going to support the base. We have enough foundation there to actually keep the component from ever moving. This come from a refinery I was working at. This was a construction practice for all their pumps. They actually put a concrete foundation 3 feet down on the ground. They actually put the base on there, level the base, and then they filled the center up, or the hole underneath the pump base and out to the edges with an epoxy grout. So they had a nice, perfectly level surface to start with to mount their pumps and motors. So a good construction practice. Here you see these pumps were regrouted using epoxy to correct alignment and vibration problems. Now, I'm wondering sometimes what they mean by they poured a different base to correct alignment and vibration problems, which means that probably that this pump had vibration issues just from in the 3 times area from movement of some of the components. So here we have to make sure we're doing it for the right reason, we're doing it the right way. But there's some keys behind this grouting process that I want to make sure everybody understands when we do regrouting. And we'll get to those here in just a second. Here we have a foundation base for a pump and a motor where there's no support in the middle, which allows the base to vibrate a little bit while the component's operating. And this happens especially when you don't have a balanced rotor in the motor and you don't have a balanced impeller in the pump. So, and maybe some misalignment, but we cause vibration, which will cause the center of this base to move around a few thousandths and cause issues with wear. So, grouting practices to eliminate vibration alignment issues. Yeah, you can say we're doing it for that reason, but you know, does this work really perform correctly? Is the grouting process really a reliable process? And I think it is if we follow some other rules. So, if we're grouting, does that actually eliminate vibration? This proper alignment is actually eliminate, the steps taken to get to proper alignment just by doing the grouting process. So my question on this one is, what happens if you have an unbalanced motor and you have an unbalanced pump? We have an impeller in that pump that's not been precision balanced. And by that I mean, if we go buy a standard motor today, or we buy a standard Gould's or FlowServe pump, I always ask the question, are those two components precision balanced? And the answer to that question is no. The pump is balanced to an ANSI standard of 0.08 to 0.12 inches per second. That's not a precision standard. The rotor in the motor is balanced to an ESA standard of 0.08 to 0.12 inches per second. And a lot of those I've checked in the past. I've taken brand new motors out of the box. I've ran a vibration check on them, and I once found a 150 horsepower Reliance motor that the vibration was 0.28, brand new out of the crate. I found other motors that were 0.18, so they're way outside the specification. And the reason we don't know this a lot of times is because most of us don't check new equipment. We assume it's new, that it's got to be good, and it meets the standards. Well, some new specifications you can apply when rebuilders, or if you buy a Toshiba motor, the balance standard should be 0.05 inches per second or less. If you buy a brand new Gould's pump or a brand new FlowServe pump, you can actually give the pump manufacturer that specification to balance that impeller to that specification before you put it in. Now back to this question. So let's say we put our unbalanced pump, we put our unbalanced motor on this perfectly and rock solid grouted concrete base. My question is, where do the vibration, imbalance, and misalignment, where do those forces go if we have this on this real rigid base? Do they just disappear? And they really don't. Those forces have to still go somewhere. They're still there due to balance and misalignment. And what happens is those forces are directly transmitted to the bearings. So you end up not getting extra life. You end up having the same failure rate, the same mean time between failure, because we really haven't done anything to eliminate the forces. We've done something to eliminate movement. But sometimes I tell people that movement may actually help you if you have something that's out of balance instead of having it on that rigid structure. So I'm hoping that makes sense. So I put this real life example in here. It says if you have a 12-inch impeller, turn it at 3,600 RPMs. If the impeller is out of balance by only 1 ounce, the 1 ounce equals an unbalance of 275 pounds of additional force. If the bearing in that pump was designed for 1,000 pounds, that actually reduces the bearing life by 48%. So you can see there just a little bit of imbalance is going to greatly reduce bearing life. And now if we add misalignment to that equation, now we reduce bearing life even more. I won't spend much time on this slide. I put this slide in there so you guys, if you can substitute your own numbers, your own speeds, your own sizes. You'll always have to call your vendor to find out what the bearings were originally designed for, but you can actually do this calculation on your own. So again, what happens to the forces of misalignment? They have to go into the bearings. So does a new foundation, the new base automatically align it to perfection? No, they help the situation, but there's some other things that go into reliability around that. So the energy forces still exist in the same magnitude. We're just applying to the forces more directly to our rotating components than we did before. So you're still going to have a high fail rate. So it's a better process to adapt. Purchase precision balanced motors. If you're rebuilding motors, make sure you give the motor rebuild shop a balance spec when they rebuild that rotor of 0.05 inches per second or less. When you're purchasing brand new pumps, you're having pumps rebuilt. Balance the rotor in the pump to less than 0.05 inches per second. And this is going to add years and years to the life of your pump. Make sure you're actually performing precision alignment. I'll show you some slides where a company spent a lot of effort. They bought the best tools you could buy for precision alignment, but they didn't follow the alignment practices and world-class techniques. Always use precision during your installations. So what's precision alignment do? It reduces energy, reduces coupling wear, reduces bearing wear, longer life cycles on your equipment, and the list goes on. So it's a practice we have to do. But in just going around the last 3 years, I've only been at a couple plants where they're actually doing precision alignment correctly. They were doing what they call precision alignment, but not following the practices was not giving them actual precision alignment. I'm hoping this slide comes out. This was from a power plant outside of Cincinnati. This is a 150 horse motor. I watched some maintenance guys, 3 of them, they were at this motor for about 6 hours with one of the best laser alignment tools you can buy. At the end of the process, I was there working on some other projects, but at the end of the process, I walked over and asked the question, how'd the alignment step go? And he said it went perfect. I've got smiley faces in all 3 planes. So I said, what's the smiley face actually calibrated to? Well, 3,000ths. So I said, oh, that's good. And I said, what do you do with the data? I'm going to take this data and download it into my CMMS system. You know, good practice. So when they left, I took a picture of this pump. So here you can see on the right-hand side, the bolt doesn't even come through the nut, which is an issue. They didn't have a torque wrench at the job site, so they didn't use a torque wrench to tighten anything. If you look at the left bolt and nut, the washer's actually squeezed down into the hole of the motor. The base was never cleaned off, and they reused the shims. And again, one of the standard or the best practices for a motor base, it should be within 75% of the thickness of the motor foot. You can see here how thick the motor foot, and you can see how thick this 1/2-inch channel iron base is. You can even see that the base is bowed. So lots of practices here that are not going to gain him any precision. And then I asked the question, how did you move the motor around to get it within 3,000ths? Well, if you look at the 2 little marks here, I hope you can see my arrow, but there's 2 marks on the side of the motor, and they used a brass punch and an 8-pound sledgehammer to move this motor around during the alignment process. So knowing what I know about alignment, this motor was probably in alignment until about 2 or 3 seconds after they started it. Then it was out of alignment and probably had some good vibration due to the structure that it was on. But again, this motor's going to fail in 6 or 8 months. They're going to go look at the data and say, well, it can't be alignment because it was aligned perfectly. But again, lots of bad practices here that would argue that this is not precision alignment. But it's a good attempt at it. It's probably better than a straight edge and a credit card, but again, following good alignment practices. So implementing a laser alignment precision alignment program without proper training is unreliable. You know, is the training just the one day on site when you buy the tool? Is the training watching the videotape that they send with the tool? Is the training, well, every time they do it, they're going to get better as they do alignment? You know, that's probably not good enough if you're really looking at precision alignment and you're looking at long-term reliability. So this is, again, another example of, you know, trying to do reliable tasks and maybe the effort's not going to have a payback. If you look at an electric motor, and I always ask the question when we're talking about precision alignment, you know, what do the bearings in an electric motor actually do? There's a number of answers, like they support the rotor, they keep the rotor from touching the stator. And some of those answers are true, but the real truth of that is the bearings keep the rotor from touching the stator when the motor's not running. When the motor is running, if you have proper alignment, the bearing will stay in the center of the stator due to the magnetic field. Now, I proved this to my maintenance people at the plant I came from. I took a 10 horsepower electric motor that had a balanced rotor in it. I took the end bells off of that electric motor, had it bolted to the shop bench. I actually took lay stands to put the center of the rotor in the center of the stator and had the lay stands holding the motor. Now I had the electricians wire the motor up and turn it on. And then I took the lay stands away. And what happened to the stator was it just stays in there, or what happens to the rotor stays in there and runs in the stator in that magnetic field. You don't need bearings to keep the rotor in the center of the stator. So at the end, and I caught the shaft, stopped the motor, but what I was trying to explain to my guys is if we do precision alignment, the bearings in electric motors should never wear out because there's no load on them. Now, making sure you follow all the steps of precision alignment using thermal growth and things like that are all the techniques we have to follow. But again, there should never be bearing wear on a motor that's precision aligned and precision balanced. So motor bearing should do nothing when the motor's running if it's a direct coupled application. Now, if you're going to hang a shiv on the end, a sprocket on the end where it's actually pulling on the motor shaft, we're going to have some bearing wear there, and we need to make sure we have the right bearings in place. So precision alignment, you know, lack of understanding here, lack of understanding precision alignment, not correcting soft foot issues, improper methods, improper no training, not calibrating the tool. I was at a plant where they hadn't calibrated their laser alignment tool for 3 or 4 years, and we actually sent it in, the tool was out of alignment by 0.008. So again, they're doing precision alignment with an uncalibrated laser alignment tool, leading to unreliability. So getting the number to the database is an important step, but what are the numbers? Are they actually real and accurate? Some other silver bullet processes, people that start the TPM process. Just saying you're going to do TPM and actually trying to get TPM done is a big step. So making sure you understand what TPM, and the key thing there is making sure that everyone in the plant, down to the operator, knows what TPM and knows what the effort's going to be. Now, I can't mention the company name, but they started their reliability program about 6 years ago. They went from 52% OEE. They're at over 92% OEE now, and they're trying to get to 96. Well, it may take them another 5 years to get from 92 to 96, but the effort we're making there, it was a union facility. We couldn't ask operators to do maintenance, but we did some operator care training where we trained the operators on every single component on their lines. Every bearing, every motor, every chain, every belt, all those equipment, how those can fail. And then part of this program was not maintenance, it was called operator care. So operators did inspections, they were able to communicate with maintenance more effectively. Maintenance knew things about things that were happening in the equipment much earlier. We bought their operators some tools to do some checks like strobe lights and temperature guns and things like that. So that was an operator care program that was very similar to TPM. RCM, the biggest failure with RCM was I do RCM analysis, but very seldom do they implement the things you find from RCM. So that makes it one of those processes that could be good if you follow all the steps. Again, I said lean maintenance and lean manufacturing. Those processes are very good, but you have to be reliable before you can be lean. So again, understanding what you're trying to accomplish and what has to be in place to start a new process is key when you're building these reliability programs. So TPM, not just the process of giving an operator a maintenance task and expecting the equipment to run better, last longer, be more reliable. It takes written procedures. It takes training programs and following the proper steps of TPM. These are processes that are key to making that successful. Now, how do I know just from other industries that written procedures and training programs work? One of the things that I look at is I always look at the U.S. military and I ask people, how old is the maintenance technician that maintains a B-1 bomber, an Apache helicopter, a nuclear submarine? A lot of times those are 19, 20, 22-year-old kids. And how do they maintain those high-dollar components without having failures? Well, the answer to that is they're well-trained. They have written checkoff lists where they do everything by a checkoff list so we don't make mistakes. And there's very, very few failures in those industries. So again, training, written procedures are key to make a TPM process work. So you must have good maintenance procedures in place to make your processes work. So I've been in a number of companies that they haven't done training for 3 or 4 years with maintenance or operations. They don't have good written procedures in place. But I hear this thing, excuse me, at many facilities where, Bob's fixed the equipment 100 times. He's our expert on fixing the equipment. Well, if you've fixed it 100 times in 20 years, maybe he's not the expert. Sometimes we assume they are, but some good training, some good procedures in place may make the equipment last a little bit longer. If you're doing lean maintenance, I went into companies where the company's done lean maintenance and they haven't gotten maintenance involved in it. That's an unreliable step. I was at a company where they put on all this food processing equipment using lean maintenance and lean manufacturing techniques. Well, there wasn't any way for the maintenance guys to do their PMs. We had to actually unbolt a machine and drag it out on the floor to be able to get in it to do some maintenance. Not very effective, but again, if we had involved maintenance, we might have found those issues a lot earlier. And I always tell people, and I'll repeat it again, you can't be lean until you're reliable, so you have to have processes in place to get lean. Reliability center maintenance, a process developed to determine failure modes of equipment components. So if we know specific failure modes, we can develop methods to predict, prevent, or eliminate those failure modes. The process involves knowledgeable teams that know how the equipment components in the plants fail. Some good documented failure information from your CMMS system. Very few plants I go into have good documented failure information. Making sure you have OEM information available. There's a lot of plants I go to where there's no old manuals on the equipment, no OEM manuals around. It's hard to know how equipment actually works and how it fails. So again, understanding how things fail. One of the classes I do at many companies, I just did it this week for a company, is equipment failure modes training. So we go over motors and bearings and what are all the failure modes of that, which ones are related to your plant, and how we recognize them. And then we go into how we prevent them with preventive maintenance tasks, how we can predict them with predictive maintenance tasks, and sometimes how you eliminate them by redesigning or doing things differently. What's the biggest failure in RCM? When I do RCM analysis, you spend all the time, the effort, and we never implement the RCM. I think in talking to Doug Pluck that over 50% of the people we do RCMs with, the RCM's never fully implemented, so you don't see the success from it. I threw a few slides in here getting toward the end. This is a study that was done, and we did this at the plant that I came from, or the company I came from. But where are all the failures in equipment? Well, it says here 25 to 35% of all equipment failures are originally engineering and design failures. You know, poor equipment selections is one of them. Improper sizing of components. An example of that was, you know, sizing belt drives on fans. Sometimes if you ask a fan company or Motion Industries to do that, you know, the calculation may come out to 4.3 or 4.4 belts. Why did they give you 4 instead of 5? That's an unreliable design. You know, poor foundation base structures, not understanding factory alignment balance. You know, I put some equipment in for a company, and I said, you want me to hire somebody to do the alignment step? And they told me all the pumps have been aligned at the factory. Well, it doesn't work that way. When you ship them, move them around, and bolt them down, they're not in alignment anymore. You know, this year we spent a lot of money at the company I came from finding out who makes the best motor, who makes the best pump, who makes the best of all these things we use in our plants. Once you know who makes the best, do we put that on all of our equipment? No, we put it on our high dollar, or maybe our top 10 or 20% of our equipment to reduce failures and reduce large downtimes. Look at this, 10 to 20% of our failures just in fabricating the equipment. A lot of times we have companies build structures and build equipment for us. And here's some of the reasons here why equipment fails early due to fabrication. You know, picking points, tie downs, the way we move things around our facilities when it gets there. So lots of fabrication type failures. Here's a company that built these big pump skids, and I just took this picture here, but we put these pump skids in. They were probably 18 feet long, 3 pumps on them, bolted. They only bolted at each corner. Well, those systems there, when I started them up, there was lots of vibration, lots of resonance between the pumps. So we had to add clips to bolt them down the floor. We had to fill all those areas up with grout. There was just way too much resonance and movements in the frame. Installation. You know, sometimes we say, well, we know our contractors are good at installing things. We hire the people to put things in, but 10 to 25% of your failures are in installation practices. You know, grouting, improper grouting techniques, improper anchoring techniques, piping strain, thermal strain, conduit strain, coupling alignment. It's all installation things. Improper lubricant on the first application. And I always tell people, if you're doing lubrication excellence, the very first lubricant you add to new equipment should be the cleanest it possibly can. It should be filtered down to 3 microns, no particles, no moisture. That's where you get the biggest bang for your buck with lubrication excellence. Here you got no precision alignment or balance standards, you know, when you're installing equipment. So again, lots of failures there. Your outside contractor, your maintenance people, do we have bad practices like beating couplings on a shaft that are actually destroying the bearings inside? All installation failures. Now we get into operations. It says 10 to 20% of our failures are from operational issues. You know, starting equipment under a load, close and discharge valves too fast. Your operations people not putting their hands on things, checking thermal conditions, vibration conditions, not checking oil levels. Operating equipment in manual. Lack of fluid to the pump on startup. You know, putting water on components. You know, and an operator one time was going through a plant. The motor thermals was kicking out on a motor that night. His solution to that was to duct tape a water hose on an electric motor. Well, there's something wrong besides just the thermals kicking out to cause them to kick out. And then running water on electric motor is not a good plan. Lack of a TPM program so operators know what to do. And then it gets down to the final one here. 20 to 30% of our failures of equipment are maintenance related. You know, improper inspection, improper lubrication practices, no or poor preventive maintenance program. I mean, if you look back at your preventive maintenance plan, how many of your maintenance tasks say check the pump? You know, what does that mean? Check the conveyor. We have to tell them what they're supposed to be checking and why they're checking and what they're supposed to do if it's out of alignment. I had this conversation this week with a group I was training. You know, when you do a preventive maintenance task, what I always told my people, I want you to find something. If you're not finding anything, maybe the task is not even applicable. So no report predictive maintenance program, no report proactive maintenance program, improper training, no procedures, no training programs, no follow-up, no retraining. All parts of making maintenance unreliable. So I put that study together, and then I found this a few years ago. This was put out by the Hartford Steam Boiler Insurance Company. It says almost 50% of all work orders are preventable. Some of the same similar numbers. It says engineering design, 42%. Operational failures, 26%. Maintenance failures, 28%. And then they got this one down here that says management issues are 4%. Well, you know, I always said the company I came from, you know, probably 80% of all that is management. Well, they just have to figure out how to correct all the issues before them. But management's responsible for a lot more than 4% of unreliability at a plant. You know, what about the effort of getting PDM started at your plant? We start PDM programs. We start buying PDM tools, predictive tools. We start hiring contractors. Well, some issues with PDMs is not reacting to the data. And I got a slides mixed up in here somehow, but we don't react to the data. So your PDM's technologies aren't effective, and they don't have a payback because we don't react to what the data is telling us. Lubrication excellence. Some unreliability issues with lubrication. Not having procedures to receive and store the lubricants. Drums sitting outside. Drums are stored in dirty areas. Not filtering the new and existing lubricants. You know, a lot of the new lubes you buy, excuse me, are dirty, and they need to be filtered before we ever take them out and put them in the equipment. No oil analysis program in place to even monitor the lubricants. And when I do a lube audit, I always pull samples out of the new drums. People say, why are you sampling the new oil? Well, because it's not clean. Sometimes the additive packages are supposed to be in there and out there. And then an analysis program around the plant to properly sample the equipment so you know when the lubes needs to be changed, when it may need to have something done to it like filtering particles, filtering moisture. Because many times you'll find out from your oil analysis program that there's really nothing wrong with the lube, but it's all the things that are in the lube that we could take out. The lubricant may still be good, but sometimes we throw it away or we change it just because the lab analysis comes back and we don't really know what to do about it. And then many plants I go to, I ask them if they're doing oil analysis. They are, but they don't understand what the data is telling them. They don't understand if you go from an 18, 16, 15 to a 21, 19, 18, then that's like 100 times more particles than you had before. So we have to understand what the ISO codes mean. We have to understand some cutoffs for moisture, for oxidation, for viscosity, which are all things that could change in our process. So we have to understand how to analyze that information. So again, as we wrap this up, looking at this curve, you can see there's a lot of things on here. We didn't get through many of them today, but we got through some of the key ones, is making sure you look at what you're doing in reliability and make sure you understand all the things around that can actually make you as unreliable, or you won't really gain much effort from it. So again, if you have questions, I don't know if we have time to take a few questions. If you've got questions and you want a copy of this presentation, you can shoot me an email. I think my email's on the front page. But definitely get the questions over to Test Oil, and they'll get the information to me. So.
All right, Terry. Thank you so much. That was great. I learned a lot. I don't see that there's any questions yet, but if they come through, I'll be sure to let you know.
Okay. All right. Appreciate that. I appreciate everybody's time for getting on the webinar today.
All right. Thank you so much for your time, and again, thank you everyone for joining us.